So we've been looking at some of the useful matrix operations available to us in Matlab, and we want to look today at solving some simple problems using those operators and those methods. So pulling up the first example here, we've got a simple mixing point. So the problem looks like this. In this problem we've got two streams, P1 and P2, which mix here, and the resulting stream P3 goes off there, and we've got different compositions in these two streams because we've got a mixture of components A and B. So let's look at the problem here. As I say, two streams P1 and P2 mixing at this point M1 to give P3, and we've got component A that's inside these streams. So the mass fraction of component component A in stream I is XAI, and we know the mass fraction of component A in these two streams. So if we've got 20% of the mass of this stream being component A and 70% of the mass of this stream being component A, then there will be a certain other mass fraction occurring in this stream here, and that of course depends on the relative mass flow rates in all these streams. So of course this is a very simple problem which we can solve by hand, so to say, but we're going to look today at solving it by vectorizing the resulting mass balances and using our matrix techniques to to develop a solution there. Right, let's just make sure we've got all the information. So we are summarizing it here. We're saying the mass fractions of A in these two streams are 0.2 and 0.7. That's kilograms per kilogram. And we are requiring the exiting mass fraction of A to be 0.6 kilograms per kilogram. So we know the mass fraction in that stream as well. What we really want to determine is the mass flow rates in these streams that accomplish that set of mass fractions. So we want a total exit mass flow rate here in the range from 2 to 25 kilograms per second, right? That's a mass flow rate. So we want to know what the total mass flow rates must be in these two streams to accomplish that. So in this problem it says find it using manual substitution, and in the second approach by vectorizing and using matrix inversion. So let's do that. And first let's generate a system of equations. So here's the formulation. We can talk about the degrees of freedom in here. Those are the variables, right? We've got three mass flow rates and we've got three mass fractions. But these variables are known. We know what the mass fractions are in each of these streams. And in fact, we know one of the flow rates. We know the flow rate must be in the range 2 to 25, I think it was. And so we want to determine what these other mass flow rates should be. Okay, so we can write our material balances first of all. So let's say we ask for the material balance of component A. So we can see here this is a simple mixing problem. We've just got component A coming here, component A arriving here, and it goes off there. So there isn't reaction occurring in the system, and so we don't expect any matter of A being translated into some other type of matter. So we can say simply that the mass flow rate of A here plus the mass flow rate of A there must equal the mass flow rate of A in there. In other words, the mass fraction of A in stream 1 multiplied by the total mass flow rate must be equal to, equivalently, the mass fraction of A in stream 2 times the mass flow rate of stream 2. That's what's coming in, and that must be equal to what's going out there. The mass fraction of A in the outlet stream times the mass flow rate of that outlet stream. We note also that this relationship does imply that there's no hold-up in the system. There's no time delay between component A exiting here and component A arriving in these two streams. So there isn't an accumulation term, there isn't an unsteady term here. This is an instantaneous mass balance, a steady state mass balance here. So that applies at this point M1. Right, so that's what we get from the mass balance on component A. Then we can also write a total mass balance for the system In other words, the total mass arriving here plus the total mass arriving there must equal the total mass going off there. So we can write m1 plus m2 is m3. So when citing this variable name, I just say m1, but of course more strictly it's m dot 1, right? This is a mass flow rate. That's kilograms per second. So these are rates. So just to emphasize that, we use the dots. Remember, dots usually denote the time derivatives. We've got m dot I. That's the mass flow rate in stream I, and that has, generally speaking, the units kilograms per second, right? That's in SI units. So in the first approach, we can try to eliminate this m dot 1, right? You see here in this equation, we've got this form here, and we've got the relationships between the mass flow rates here. So we can say m dot 1 is equal to m dot 3 minus m dot 2. So we can substitute for m dot 1 in this way, and so we can write m dot 2 has this relationship with m dot 3, and so that's quite easy, right? We do know what the ranges are for the flow rate in stream 3, right? 2 to 25. So we could simply pick some values from 2 to 25 in there. Then we know all the mass fractions here, so we can simply substitute those values in, and that will yield to us the mass flow rate in stream 2. And if we know the mass flow rate in stream 2 and that in stream 3, we can simply calculate the unknown remaining flow rate that's in stream 1. So that's a very simple approach there. That's how we can solve manually, so to say, for the mass flow rates coming into the system. So we can write the code for that. Well, let's just do it ourselves here. Let me just resize this. So we say that the stream 3 is in the range 2 to 25. So let's say M3 is linspace 2 to 25, and let's just use 30 points for that. And we want to calculate M1 and M2. So we know that M2 is equal to, and M2 requires all these values here, these XA values. Sorry, let's look here. M2 requires all these ones here. So we already have values for these M3s here, and we do know the mass fractions in each stream, so we are able to provide all these X values here. So we are in fact able to calculate m.2 if we just specify the values for X. So let's switch over to our program here, and let's specify those values. Let's do it as a vector. So let's create XA being equal to, and if we look at the original problem statement, we have here that in the first stream we have 0.2, the mass fraction is 0.2, we have 0.7 here and 0.6 for the last stream. So that's our vector value, 0.2, 0.7 and 0.6, and so we can calculate M2 here as being x3 minus x1 over x2 minus x1. So that's xa3 minus xa1, that divided by xa2 minus xa1 again, and that times m3. So that's our m2. So we have the vector m2 stored here, and then the remaining unknown is m1, which we know we can get just from the difference. m1 is m3 minus m2. So let's plot all that. Let's plot these against m3. So we can plot m3 comma m1, and let's plot let's use x's for those, maybe x dashes, solid lines with crosses on it, and m3 against m2.